So for a vehicle, the speed time graph is given, and we have to have the we need to have some commentary on the speed time graph. And let's assume that the object is traveling in a straight line, so we can use the word speed and velocity interchangeably. So let's talk about for the first 10 seconds in this interval. Now, the first 10 seconds, this is a tricky one because basically you have two kind of curves in the first 10 seconds. First, the curve increases, it gets steeper, and then towards the end, the curve decreases, it gets more and more horizontal. So from speed time graph, we have to comment on the acceleration and speed. So first, from 0 to 10 seconds, first of all, if we talk about the speed is being increased from 0 all the way to 10 seconds. The speed is being increased. If it is velocity, velocity is being increased. But the speed is increasing in two different ways, at least in two different ways. But if you want to consider the middle part, when you have a straight line, you can consider that one as well. But let us talk about these two important parts, the first region over here, the second region over here. So the first, at first, speed increases, but with increasing acceleration. And towards the last few seconds of the 10 seconds, it could be like from 6, 7, 8 to 10 seconds, it increases again. It increases again, but with decreasing acceleration. So it increases again, but with decreasing acceleration. It doesn't mean the speed decreases. So if I'm to draw the table would be something like this. So let's say we have time 0, 1, 2, 3, 4, 5 to 6, 7, 8, 9, 10. Let's go all the way to 10 seconds. And here we have speed in meter per second. So at 0, the speed could be 0, and then the speed could be, let's say, 5, then 20, and then, okay, let's make it easier, 10, and 30, 30, 40, let's say, and 50, 60, 70 here, and then we can go with 80, let's say 90, 95, 97, and then 98. So it could look something like this. So you see, initially the speed was increasing with at an increasing rate. The change was plus 30, and after a while the change is constant. So this could be the central part when you have a straight line, the part with the uniform acceleration, the central part, this one where the change is constant. But towards the last few seconds, you see the speed is increasing, but now the change is only 5, and after that the change is only 2, and after that the change is only 1. The increase is only 1. Speed is increasing still, but now it is increasing at a decreasing rate. That is called speed is increasing but with decreasing acceleration. So the first part is kind of tricky. What do we have for 10 to 30 seconds? That's very simple. The speed is uniform in this part, 10 to 30 seconds. So if the speed is uniform, can I say, and the object is not even changing the direction, so we can say no acceleration. And from 30 onward second, in the last part, is the speed increasing or decreasing?
So it's decreasing.
It is now decreasing. So speed is decreasing after 30 seconds or 30-second onward. Speed is decreasing. Is it decreasing at a uniform rate or non-uniform rate?
So uniform rate.
Uniform rate. So can I say it is increasing with uniform deceleration? Because deceleration would mean the speed is decreasing. But since it is decreasing uniformly, so we say uniform deceleration. And keep it in mind, for deceleration, there is only one kind in your syllabus, that is uniform. But the deceleration can also be increasing and decreasing. So we can have increasing deceleration and decreasing deceleration, but that is not part of our syllabus anymore. Okay, so let's do once again a qualitative analysis on the other graph. So from 0 to 10 seconds, we have a curve. It may not be very clear, but if I could zoom it in, we have a curve that looks something like this from 0 to 10 seconds. So we have to comment on the speed and acceleration. Keep it in your mind, whenever you have speed time graph, you have to comment on the speed as well as on the acceleration. When you have distance time graph, then you have to comment on the speed only. So speed is increasing first of all, but since you have a curve that is curving upward, it's getting more and more vertical, so speed is increasing with increasing acceleration. And after 10 seconds all the way to 30 seconds, what we have is a straight line from here all the way till 30 seconds. We have a straight line. So is the speed being increased from 10 to 30? Yes. Then the question is it increasing at a constant rate, at a uniform rate, or in non-uniform rate?
Uniform rate.
Uniform rate, very good. Speed is increasing. So if it is increasing with uniform rate, can I say speed is increasing with uniform acceleration? 30-second onward, still the same case. Speed is decreasing with uniform deceleration. All right. So here we have another speed time graph. So refer to the speed time graph, complete the table. We have to comment on the speed and then we have to comment on the acceleration. I'm going to label the segments. Let's call this one segment 1, 2, 3, 4, 5, and 6. 5 is not in the syllabus anymore, but we'll just make a comment on it uh, without too much indulging in that. We need to comment on two things. The first column is for the speed, the second column is acceleration. In the segment 1, in this part, what happens to the speed, what happens to the acceleration, this is what we have to point out. So, for example, in the section 1, in the segment 1, I can clearly see that the speed increases and the acceleration is not uniform, rather, the acceleration also increases. So, speed increases, acceleration also increases. Let's take a look at the segment 2 over here. So, on the segment 2, what happens to the speed?
Sir, it's uniform.
So, if the speed is uniform, what's up with the acceleration? There would not be any acceleration because we have assumed the object is traveling in a straight line. It's not even changing the direction, so the velocity is also uniform. So acceleration in the segment 2 is 0. Let's take a look at the segment 3. What happens to the speed? What happens to the acceleration? So since I can clearly see the line going upward, it means the speed is being increased. But then it's increasing at a constant rate because we have a straight line, the gradient would be constant, and the gradient of speed time graph gives you the acceleration. So acceleration is not increasing, acceleration is constant, and you can also say positive. But let's ignore the sign convention. We say the acceleration is constant. Let's take a look at the segment 4. What happens to the speed at segment 4? It decreases. So acceleration in this case is basically your deceleration. What kind of deceleration? Since you have a straight line going downwards, it is uniform deceleration or constant deceleration. So for the first one, you can write previous one, you can write uniform acceleration or constant acceleration. And for this one, you can write uniform deceleration. Okay, let's take a look at the part 5. This is kind of tricky. Now, first of all, what happens to the speed? Is the speed increasing or decreasing?
Sir, decreasing.
Okay, the speed is decreasing. Let's write it down first. The speed decreases. Then the follow up question is, if the speed is decreasing, is it decreasing at a uniform rate or non uniform rate?
Sir, non-uniform.
Okay, we can write it first. The speed is decreasing. Very good. Non uniform rate. So the deceleration is non uniform. Non uniform deceleration. Like I said, for non-uniform deceleration, you can have two options. It could be decreasing deceleration, and it can also be increasing acceleration. Whenever we have something as non-uniform, it can always have two options. It could be increasing or decreasing. So let's see, how do we find out? All we have to see is the gradient. Check out the steepness of the line here and compare it with the steepness of line at the end. So what do we see? At the start of the line, or I should say curve, the line was more of a vertical. It was steeper. It was more of a vertical. But as we go towards the end of the line, you see it's becoming more and more horizontal, which means it's getting lesser, less and less steeper. And eventually we can say the gradient is being decreased. If the gradient is being decreased, we'll say it has decreasing deceleration. But once again, I mean, a maximum of non-uniform deceleration is enough for our syllabus. We don't have to specify what kind of non-uniform acceleration. But just in case, if you have to answer that, you check the gradient. If the gradient is being increased, it would have been increasing deceleration. But in this case, the gradient is being decreased. You see, this is the shape of the curve. Initially more vertical, and towards the end more of a horizontal. So we say decreasing deceleration. The last one, part 6. Let's comment on the speed first. So in the part 6, what happens to the speed? Increases or decreases?
So decreases.
And the speed decreases. So we have deceleration. What kind of deceleration? Uniform or non-uniform?
Uniform.
Uniform deceleration. So at the end, I'm going to just draw the table for the part 5. Because since we're done with it, so I'll just draw the table. So if we have time here and speed over here in meter per second, so 0, 1, 2, 3, 4. Let's compare the speeds at 4 intervals to understand why do we have such a shape in the part 5. So this is just for part 5, for the segment 5. So initially the speed could be, let's say 20. Then the speed is, say 10. Or let's make it, yeah, let's say 10. Then 5. Then 3. Then 2. Let's comment on the speed. The velocity or the speed is being decreased. But what was the decrease first in the first second? The change was, or there was a drop of 10 meter per second. The change was 10. It decreases by 10 meter per second. What's the change in the next second? 5. What's the change in next second? 2. What's the change in the next one? Only 1. So the velocity or the speed is being decreased, but initially it was decreasing faster, and then it decreases at a slower rate. And if we extend this one, I mean, if I extend this part 5, if it is extended into something like this, the line becomes horizontal. What does that mean? It means beyond that time, the speed would remain same. So initially it was decreasing quickly, Afterwards, it would decreasing at a slower rate, and eventually, it's not even decreasing. If only if we had a horizontal line, a pure horizontal line with this one, but we don't see it here. They haven't made the line horizontal. So the topic that we have for today is how to find displacement in acceleration from velocity time graph. And we can say the same thing as how to find distance and acceleration from speed time graph. Because like I told you in no level physics, in graphs we assume that the object is traveling in a straight line. So distance means displacement, speed means velocity, unless it's mentioned otherwise. So both of them can be used interchangeably. So for the first part, how do we find the displacement or distance from speed or velocity time graph? And the answer to that question is, in order to find distance from speed time graph, we have to find area under the line or area of the graph. So for example, if they ask us what is the distance covered by the object in first 4 seconds, so we can draw a line up till 4 seconds, and then we can find the area of this shape, area under the line, area that is towards the time axis, area between the line and the time axis. So this shaded area, whatever shape that is, in this case it would be a right angle triangle. We apply the rules of mathematics, the area formula for the area of that shape, and we can find the area, and that area would be the distance. But the second case, if you want to find the acceleration from speed time or the velocity time graph, we simply find gradient of the line. If the graph is a straight line, you can choose any of the 2 points to find the gradient. If the graph is not a straight line, rather the graph is a curve, for example this is, let's say, the speed time graph. They ask you to find the acceleration. Now the first thing is, in this kind of situation they would always ask you to find gradient or find the acceleration at a specific interval of time. So let's say they ask you to find it 5 seconds. So at 5 second mark, over here you draw a tangent, and then you find the gradient of that tangent. But this is the advanced case that we'll be solving afterwards. So take a look at the graph that we have, speed time graph. In the first 4 seconds, there is uniform acceleration. Then from 4 to 14 seconds, there is no acceleration. Then from 14 to 16 seconds, there is again uniform acceleration. And that uniform acceleration, this uniform acceleration is greater than the first one, because in the second case, from 14 to 16 seconds, the line is steeper. We need to find acceleration from 0 to 4 seconds, and we need to find the displacement. Acceleration would be gradient of line, displacement or distance would be area under the graph for the first 4 seconds. So what do you do in this kind of case is, you draw a straight line up till 4, like this, and now we simply need to find area of this shape. if I'm to find the distance or displacement. So let us find the distance first. So distance in this case equals to area. All right. So area equals to, this shape is a triangle. What is the area for a right angle triangle? What's the formula?
So 1 over 2 base multiplied by height.
Okay, 1 over 2 into base into height. So 1 over 2 as it is, or 0.5 times the base is 4 and the height is 5. So 5 fours are 20, divided by 2 would be 10. So the answer to that question is 10 with the unit of meters. So the displacement is 10 meters. Or think of it as distance. Assume that it is a speed time graph. Up next, we have to find the gradient. In order to find the gradient, I can use the formula of gradient, that is, the simpler one is rise over run. So I need to find gradient of the line. So gradient equals to, represented by m, the symbol for the gradient is m. So m equals to, what is the rise? Rise means the vertical distance of that line, 5, divided by run. Run means the horizontal distance covered by that line, which is 4. So what is the answer to that one? Simply 5 divided by 4, which would be 1.25. So the gradient of this one gives you the acceleration. Gradient equals to the acceleration, and that equals to 5 over 4, which is 1.25 with the unit of ms minus 2. Let's take a look at the next part. From 4 to 14 seconds, we need to find acceleration and then we need to find the displacement. Finding acceleration is very easy. 4 to 14 seconds, the graph is a horizontal line. Acceleration equals to gradient. What is the gradient of the horizontal line? It is 0. The gradient of the horizontal line is 0. Gradient is the steepness of the line. So the line is not steep at all. So the gradient would be 0. Or even if you use the rule, this line has no vertical distance. I mean the start point and the end point. Think about these 2 points. There is no rise of the end point. The end point is at the same height. So rise is 0. Whatever the run is, which in this case is 10, from 4 to 14, the difference is 10. So 0 divided by 10, the answer would be 0 once again. But let's find the distance. In order to find the distance, we have to find the area under the graph. So I'm going to find this area from 4 to 14 seconds. So what shape do I have?
It's a rectangle.
A rectangle. And what is the area for the rectangle?
So length multiplied by width.
Length multiplied by width. Okay, length multiplied by width. You can also say length multiplied by breadth. It's just the same thing. So the length is from 4 to 14. It starts from 4, it ends at 14. So the length is 10, not 14, because it doesn't start from 0. Times the width. So this height is width, which in this case is 5. So you multiply it by 5. So 5 times 10 or 10 times 5. Acceleration was 0, and this one distance would be 50 meters. Let's take a look at the next part. From 14 to 16 seconds. Now this one is slightly tricky and many of the students make mistake in that. From 14 to 16 seconds. You need to find two things. First one, you need to find the acceleration. So for the acceleration, I simply need to find the gradient of the line. So gradient equals to rise over run. So this is the start point of the line, this is the end point of the line. What is the rise of the line? See
So
the
two,
line, right? How much?
two,
No, the rise is the vertical distance. So the line starts from a height of 5 and it reaches to a height of 10. So the rise is 5. 10 minus 5, 5. The run is the horizontal distance. So what is the horizontal distance covered by the line? What is the horizontal separation between these 2 points? From 14 to 16, it is 2. So acceleration would be equal to gradient, which is 5 over 2, which would then be 2.5 ms minus 2. Let us find the distance now. So in order to find the distance, we need to find the area under the graph. So all the area that is below this line and the time axis. So all of this area would be included. So first of all, not only that, but even this one. So all of this area would be included. Now, the pink one. What shape is that? Do you know the name of this shape? That shape is called as trapezium. We can find the area of the trapezium as well. But if you're not comfortable with this, I can consider this thing as a compound shape. I can convert it into two shapes. Check it out. So this is the first part, this is the second part. So now we have a compound shape. The first part of the compound shape is a triangle, right angle triangle. What is the area of that shape? Let's find out. So for the right angle triangle, we have the same formula, 1 over 2 base into height. So 1 over 2 as it is. The base of this triangle is from 14 to 16 2. The height of this triangle is from 5 to 10 would be 5. So the overall distance for this one is 5. The area of this shape is 5 meter square. So the distance would be 5. Let us find the area of the shape 2. Shape 2 is a rectangle. Area of the rectangle would be length. From 14 to 16, length is 2. From 0 to 5, the width is 5. What do we get? 10 from here, 5 from there. So the overall distance would be 10 meters plus 5 meters. Now from 0 to 16 seconds, we need to add the question with that. This one is slightly different. From 0 to 16 seconds, you need to find the average speed. So you need to find the average speed from 0 to 16 seconds. So the formula for the average speed is written like this. Average speed equals to total distance divided by total time. What is the total distance covered by the object? The total distance would be the sum of all three distances. So the total distance is basically this one, all of it. We didn't find the total distance all at once, but rather we have found these distance in segments. But if I add all of those segments, I shall be getting the total distance. So 10 plus 50 plus 15. So 50, 60, 70, and 75 is the total distance. 75 meters is the total distance, and the total time on the graph is 16 seconds. So what we do is hit the fraction sign, 75 divided by 16, hit it on the calculator, press SD, 4.6875 in 2SF, we can write it as 4.7. And so once again, average speed doesn't mean that the vehicle would be traveling with this speed. No, it's not compulsory. So average speed simply means whatever the speed of the vehicle was, because it was different in different segments of time. So if you average them out, then the speed would have been 4.7 meter per second.